All right, everybody. Welcome to Calculus 2. We're just going to kind of hit the ground running. This class kind of just continues where Calculus 1 left off, and where Calculus 1 kind of focused on derivatives and this notion of dy's and comparing them to dx's and infinitely small changes in things, and examining the ratio of those things to talk about things like slope and rate of change. This class is going to be all about adding things up and adding up really, really tiny amounts of things to get some big picture quantities. Now that won't really make much sense to you, but that's okay. We're just going to start this class kind of just on a fresh page, and we're going to start with a completely brand new goal that's going to seem a little bit out of left field right when we start, but the more the class progresses, the more the idea is going to make a lot of sense, and it's going to start connecting back to calculus. And so for right now, just for starters, we are going to imagine that we have the parabola. We're going to imagine that we have this parabola y is equal to x squared. And actually, we're going to make it a little bit wider just so it's a little bit easier to draw later. Okay, so here's our parabola. F of x is equal to x squared. And I'm going to claim that my goal for right now is going to be to find the area from x is equal to 1 to, say, x is equal to 5. Let's do 5. Okay, and so for no reason, right, with no real fanfare, no justification of any sort, I claim that my current goal is to come up with the area of this kind of oddly shaped shaded region. Okay, that is going to be our current goal. Again, with no real rhyme or reason, I'm going to say start off this video with an open mind that I just have a very random goal that I'm trying to set out to accomplish. Okay, so that's our goal, and rightfully so. You may ask yourself, well, how the heck am I going to figure out what that area is? And I would say that, I have no idea. But what we're going to do is we're going to start with a shape that we know really well, okay? And that shape is the area of a rectangle, right? So remember that the area of a rectangle is just equal to the height of that rectangle times the width of that rectangle. And that's a shape that I know really, really well. Okay, and so all we're going to do is I'm going to say, let's make this our first attempt. Attempt number 1. Okay, all I'm going to do is I'm going to draw one single rectangle to try and approximate this area. Now, I know this is not going to be a good idea, but I'm just going to show you how this kind of leads into where we're going. So just to kind of start off, right, if I was going to draw a rectangle, I might say, well, this is a good place to start, right? I have this interval right down here. I have that interval down there, and that might be a good place to start for the width of my rectangle. And so you might notice that the distance from 1 to 5 is equal to 4. But I need, obviously, the height of a rectangle. And so all I'm going to do is to just arbitrarily, I'm going to choose to use this left endpoint here, and I'm going to look at this point that I get located at that left endpoint. So for instance, I know my x value is 1. How do I get the y value? I'm going to plug that x equals 1 into my function and very quickly get that y is equal to 1. Now, why am I interested in knowing what that y value is? Because that y value gives me some height, right? I'm going to kind of complete this drawing, and I'm going to create a rectangle based on literally just one point. I'm going to use one rectangle, right? Use one rectangle. And I'm going to say that my area under the curve, my area under f of x equals x squared, right? Between x is equal to 1 to x is equal to 5, I'm going to say that it's approximately equal, right? It's an approximation, right? But it's going to be whatever the area of that rectangle is right there. And if we use this formula that we had from earlier, right, that the area is going to be equal to the height times the width, the height is just going to be the y value, right? The y value, which is just 1. And the width is just the length of this interval, which has a length of 4, like we already talked about. So I'm going to say that it's approximately equal, or not that part, but it's equal to 4. Okay, and say, ha, that's my answer. Now, obviously, hopefully, if you're paying attention, right, this is not a very good guess. I mean, it's a guess, and it's better than nothing, but hopefully we can kind of see from the picture, right, that we have a lot of missing space kind of in this region. And so the next question that I naturally have is, well, how could we make this guess better, right? How could we improve our guess? And the answer is, we're going to take another crack at it. Attempt number 2. Okay. Remember, our goal is to come up with the area, underneath this curve inside this interval. And we did it. We tried with one rectangle, but now let's try it with 2 rectangles, right? Let's see what happens if we get a little crazy. And so all I'm going to do is I'm going to take this interval, right? This interval down here, and I'm going to split it right in the middle. Okay. I'm going to put x equals 3 right smack dab in the center, and I'm going to create 2 rectangles from this. So the first rectangle that I'm going to make is still going to use this left endpoint. So I'm still going to use this one. I'm going to use this dot, and I'm going to create my first rectangle. So dot, 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 dot. But now I'm going to stop right when I get to that middle part. So my first rectangle is only this small chunk right here. And now what I'm going to do is I'm going to now use this new left endpoint, right? So this is like my first left endpoint, and we call it the left endpoint because it's on the left side of this interval. And now I'm going to use the next one. I'm going to figure out what point I get, right? So here's x equals 3, and what would my y value be? Well, my y value, looking at this, if I plug in 3, I'm going to get 3 squared, which is 9. And so I'm going to create a second rectangle based on this point that I just made there. So here is the second, there's the second one right there. And the question is this a better estimate, right? Have I done a better job? And so I'm going to say that my total area now, is going to be approximately equal to, if I were, let's call this first rectangle a sub 1, and let's call this second one a sub 2, if I got the area of the first rectangle and I added it to the area of the second rectangle. And so, coming up with these areas, not too bad, right? Area is still just going to be height times width. We're going to need it for the second one too. We're going to need height times width. So let's come up with those. Let's kind of zoom in here for a second. We just need to remember, okay, well, what's the height of this first rectangle? Well, the height is just given by the y value. So the height is just 1. The only thing that's really changed in this first one is the width of that rectangle, right? And so the width of this rectangle is now no longer 4, but it's going to be half of that, right? We cut this into 2 pieces. So now we have that the height is going to be 1, and the width is going to be 2. And so this is going to be the area of this first rectangle. And so if we move on to the second one, now we need to figure out, okay, well, the width of this second rectangle is also going to be 2, right? So we know what the width there is, that's 2. But what's the height? Well, last time I checked, this height is still just given by the y value of this particular point. And so the height here is going to be 9. And we just add these results together, and we're going to get 2 plus 18, which is equal to 20. And this looks like a much more reasonable estimate compared to, say, just doing just one single rectangle, right? Trying to just do it all in one go. If we split this up and cut it into 2 pieces, it looks better. Now, is it perfect? Absolutely not. Like I said before, we have some empty space up here, and we also now have like an empty gap there. But you can kind of see from the numbers that we're getting a more accurate answer. And so the question that you have to ask yourself is, okay, well, if two rectangles was better than one rectangle, right? How could we make this guess even better? And the answer is, well, we're just going to add more rectangles. So let's do this again, but now we're going to create, let's do 4 rectangles. And so all I'm going to do is I'm going to take this interval, which goes from x equals 1 to x equals 5, and I'm going to chop it up into 4 pieces. So I'm going to put a slice there, a slice there, and a slice there. And I'm going to use this same method. I'm going to basically snag whatever this point is, which is x is 2. I'm going to put a dot right there, okay? And I could write out what this point is. So this point is 2, 4. Then I could put the x value here, which is going to be 3. We already did this point earlier. This is the point 3, 9. And then I could put this x value here, which is x is equal to 4. I could put the dot for it right here. All right, so we're going to get the point 4, 16. And I am going to draw these rectangles one more time, again, using these left endpoints. Okay, so I'm going to draw a rectangle there using this endpoint. Now I'm going to skip ahead to the next one, and I'm going to draw another one using that one. So there's the top, and we stop as soon as we get to our next point. There's that rectangle. Then we're going to go on to the next one here, and we're going to draw this little rectangle, and we stop once we get to our next little split, if you will. And then our very last one all the way up there, we're going to create one more rectangle to complete our drawing, and there are our 4 rectangles. So, whoops, let's shade these guys in. So we have one here, one here, one here, and then our 4th rectangle. And I'm going to kind of call these rectangles, in a very similar manner as I did before. I'm going to zoom out here just a smidgen. And let's just say that these rectangles are just A1, A2, A3, and A4. And so what we're going to get is in our 3rd attempt, right? Attempt 3. Attempt number 3, which is 4 rectangles now. Okay, 4 rectangles. That we're going to guess that the total area that we're looking for is approximately equal to A1 plus A2 plus A3 plus A4. And we could do the same process. I'll run through it really quick. So again, the first area, they're all going to be height times width. And you may notice that the width of them now has also scaled down, right? The total interval length was 4, but now I have 4 rectangles. I've chopped it up into 4 pieces. So when you really think about that, right? So the width, if you will, the width is basically equal to the total interval length, right? It almost makes too much sense, right? It should make very natural sense. It's a total interval length divided by what? Well, it's going to be the number of rectangles that we're trying to use. And so in this case, for the first one, the height for the first point is still that y value of 1, but the width is now also going to be 1. So this is going to be the area of the first rectangle. We can do the second one. So the height of this second rectangle is going to be the y value. So we get 4 times the width, which is also 1. We can do the next one, which has a height of 9 and a width of 1. And the very last one, which has a height of 16 and a width of 1. And so this answer, we're going to get 1 plus 4 plus 9 plus 16, and that's going to equal 30. And now you may notice that this guess is getting better and better and better. And it turns out, right, these gaps are getting smaller, right? The missing chunks that we have here are not as big. We do still have them, but they're very, very small. Those gaps are shrinking in size, and we are covering more of that space using these rectangles, okay? And so the general question that we usually pause and reflect on at this point is, okay, well, We started with 1 rectangle, then we did 2, then we did 4, right? How many rectangles would get us a really, really, really good answer? And at this point, we have an idea that more rectangles, I'm going to write this down, more rectangles, more problems, right? No. More rectangles basically means that we get a better guess of what the area is underneath that curve, okay? Now, we're going to shelve that idea for a second. We're going to kind of get back to it at the very end of the video. But for right now, I'm going to introduce some notation that you would see in the textbook or maybe while you're doing some of these homework problems. So maybe I'll title this section Notation, okay? Notation. All right. And so one thing you may notice is that as we start adding more and more rectangles, right, we got the areas and we called it a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. And if we kept going, right, this would be a whole lot to write out every single time. And so there's actually a special symbol that we use to shorthand adding a whole bunch of things together when there's this nice little pattern. And so I'm going to give you a definition. So sigma notation lets us add a finite, for now we'll use finite. We'll add a finite amount of things together in the following way. And I think the best way to do this, instead of giving you a super rigorous definition, is to just do it via an example. And so what this notation looks like is, first and foremost, we have the Greek letter sigma. That's this big guy right here. And the way it works is, let's say I wanted to represent what it looks like to add up A1 plus A2 plus A3 plus A4, right? How would I shorthand this? And the way that we write this symbolically is we say, okay, we're going to start counting from 1. We're going to start counting from n is equal to 1. We're going to stop counting when we get to n is equal to 4. Okay, so we pop that at the top. And all I'm going to say, is like, what are we adding up is the stuff that goes here. And so I'm going to say, well, we're adding up all of these areas. And the way that it works, just to kind of drive in the point, is we're going to start with the number 1, and I'm going to plug that in everywhere I see an n. So I'm going to plug that in here, and I'm going to get a sub 1. Now I'm done. I plugged in that n is 1. I'm going to put a plus sign, and then I'm going to increase this number to 2 now. And I'm going to plug it in. And guess what I get now? I get a sub 2. Great. I've now done that. Guess what happens to this number? It's going to increase to 3. I'm going to plug it in. Now I get a sub 3. And we keep going until we hit 4. And so we're going to add, and we're going to add in the final one, a sub 4. And we stop at 4 because the top of this thing says stop at 4. And so this is how we shorthand writing a sub 1, a sub 2, a sub 3, a sub 4 a whole bunch of times. We can just write it in this short way. So, in what we did earlier, the shorthand way of saying, that our total area was approximately equal to what we get if we add up all of the individual areas starting with the first one all the way up through the fourth one. That's what this says. So this symbol here kind of means add up what we call a discrete amount. And this thing discrete simply means a very fancy word for meaning that we count 1, 2, 3, 4, like that we count in this particular way. So it's discrete addition. That's not super important, but the idea is that it basically means we're going to add stuff up. What are we adding up? This is the thing we are adding up. So the pieces we are adding up. Okay? And so this is sigma notation. So again, if it's like a little weird, maybe I'll give you like another example. So for instance, in sigma notation, maybe if I give you n is equal to 1 to 3, and I put n squared minus n here, then the way this works is I would plug in 1 every time I see an n. So I'd get 1 squared minus 1. That would be my first term. Now I'm done plugging in n as 1. So next up is 2. So I'm going to get 2 squared minus 2. Now I'm done plugging in 2. Now I plug in 3. I get 3 squared minus 3. And we stop at 3 because that's the number on top. And so we get, okay, I get 1 minus 1, which is 0. I get 4 minus 2, that's 2. I get 9 minus 3, which is 6. So this adds up to be the number 8. And that's how sigma notation works. Okay? All right. So that was one thing, and we're going to kind of revisit this in a moment. But let me kind of scroll back up here. These rectangles here have a very fancy name. And the name of those rectangles are, well, it's in the title. Riemann sums. So Riemann sums is the name we give for adding up all of these rectangles. Okay. Now, you may notice, actually, before I say that, I'll just go down here and give us a drawing. So I'm going to give us a drawing, and I'm going to let you do a little bit of Sherlock Holmesing of what's going on here. So I'm going to make an attempt to sketch the same thing twice. And remember in this last example, we did on this interval from 1 to 5, and here we did from 1 to 5, okay? But in the example we did before, let's go back to my 2 rectangle example. So splitting this up into 2 regions, right? 3 is in the middle here. In the example I did before, I kept saying, use the left endpoints. And I'm going to now change this to be titled the left Riemann sums. Okay? And what this means is that I'm going to use this left endpoint to be my starting guide, and it's going to let me draw a rectangle until I hit my next one, and then I'm going to use the next endpoint. I'm going to draw this, right? I'm going to use that point. I'm going to draw my rectangle, and great, right? So this is what, if we were trying to approximate the area under the curve, we would get these particular rectangles, right? This is what we did in the last one. But as you can imagine, right, I kept saying it before, right, it's kind of an arbitrary decision. You could have picked any endpoint. And so, there is also what we call the right Riemann sums. The right Riemann sums. And as the name suggests, I could have started, instead of using the left endpoints, I could have used the right endpoint. So I could have said, let's go all the way up to here and draw a rectangle like so. And I'm going to stop, I'm going to start kind of doing my drawing going this direction now. So I'm going to stop drawing my rectangle when I hit the next little sub-interval here. So there's my first one. And my second one, I'm going to move on over to this guy here, right? Again, we're using the right endpoints now. So I'm going to use this endpoint, and I'm going to create the rectangle from it using the right endpoint, just like so. Okay? And so now you may notice that if I were to use this, what we call this right Riemann sum method, okay, if I were to use this right Riemann sum method with n is equal to 2 rectangles, right, in both cases, you might notice that I would get completely different answers, okay? And that should kind of make sense, right? Depending on how I draw these rectangles, I could get completely different answers. And maybe just to kind of drive this point home, there's one more method we could have done. So let me just kind of toss one more at you. So again, I'll try and sketch my graph of x squared. Here's my little interval from x is 1 to 5. We split it right in the middle at 3. And now we could do what's called the midpoint Riemann sums. Midpoint Riemann sums. And as the name might suggest, all of our rectangles kind of have this as their base, right? This is the base of all the rectangles. But before, if I was doing the left Riemann sum method, I would use this left endpoint right here to create that rectangle. If I was using a right Riemann sum method, I might, actually, let's just stick with it. In this particular interval here, I would then switch over to the right endpoint and create that as my rectangle. But if I'm using the midpoint method, what I'm going to do is even better. Well, maybe not better, but it's just different. I'm going to use this middle point of this interval and make my rectangle like so. And so this would obviously be the point x is equal to 2. We would have to figure out this is the point 2, 4. And I would create this rectangle here. And same thing in the next one, right? So my other rectangle here would be the base of the rectangle right there. And so I would use the middle point of that little rectangle at x is equal to 4. And I would create the rectangle, my second rectangle from that midpoint right there. And this right here would be my second rectangle like so. And each method has their pros and cons. Each method will give you a slight different answer. We have different ways of estimating things for a reason. But so in the homework, for instance, you're going to get practice. You're going to be asked, to, estimate the area under the curve using the left Riemann sums, using the right Riemann sums, using the midpoint method, etc. And it's not going to be too bad, right? So the idea is exactly what we did before. Once you know your interval length, like if the total interval length is 4, but I'm using 2 rectangles, then clearly each of these rectangles itself is going to have a width of 2, etc., right? So if you read the textbook, it gets pretty technical with their jargon, but if you watch this video and you kind of understand what's going on, it's actually very easy to come up with these areas. We're just back in geometry class, adding things up, counting with our fingers. And so I promised that we were going to revisit the the sigma notation thing. And so one thing that I want to throw back at you was, if I have this sigma notation, and let's say I start with the first rectangle and I end with, say, big N, the nth rectangle, right? Where this could be any number, right? Any number of rectangles that you want to use, right? The more rectangles, the better. All right, and we had said that, if we're approximating the area under the curve, that we're just adding up all of these individual little areas, right? And that this equation would give us, take the first area, add it to the second area, ... all the way until we finish, right? Until we reach the nth area that we want to add up. But what you'll see in the textbook is a more general formula, and what they say is that, the area of any given rectangle is just, as we've said before, it's just the height times the width. And I'm going to reintroduce this drawing back here, just of this random function f of x now. I know it looks like x squared, and you can think about it as x squared, but let's just say this is a random function. Woo, come back! Let's say this is a random function f of x, and we have some interval that I'm asking, like let's say from x is equal to a to x is equal to b, and I want us to approximate the area under the curve between those values, right? So we're aiming to get that area right there, okay? How do we do it? And so the textbook says, well, we're just going to add up rectangles, right? How many rectangles you get to pick. And so they come up with some general formulas. The first that's kind of the easiest to think about is, what is the width of a random rectangle going to be, right? So if I cut this thing up, if I cut up this interval, into n pieces, right? So let's say that there's n rectangles, which means that each one of them, you know, kind of depending on if we're using the left endpoint method, the right endpoint method, or the midpoint method, each one looks like this. And so the question is, if this is like some generic a sub n, right? Some generic area of a rectangle, what's its area? That sounds super intimidating, but last time I checked, area is just height times width. And the width is not going to be too bad. For instance, again, just to give you a tangible number, if like this whole width, okay, let me get rid of this so it doesn't confuse you. If this whole width was equal to 10, and I was using n is equal to 5 rectangles, how wide would each rectangle be? Well, the width would therefore be, right, the total length divided by the number of rectangles, and each rectangle would be 2. And that's pretty much the thought process, which is, okay, well, what if this is some length, right? And by the way, what is the length of this interval, right? If we start at one point, end at another, how do you get the length? Right? If I started you at x is equal to 2 and I said that the other value was x is equal to 20, what's the length between them? Well, you just do final minus initial and you get 18. And so in this particular case, if our final value here is x is b and our initial value is x is equal to a, then this length here is just b minus a, right? It's going to be some number. That's the math you would do in your head. And now, if instead of having 5 rectangles, we just have n rectangles, then the width of each of those rectangles is going to be the total length of the interval, b minus a, all over the total number of rectangles, n, right? And again, I'll write this down. This is the interval length, right? You'll see this formula in the textbook, and I don't want it to scare you, so I'm just going to write down what it means. And n is the number of rectangles that we're choosing to use. The more rectangles, the better, okay? And so the very last bit of this puzzle is, well, what is the height of any of these rectangles? And the height, you know, kind of depending on which method we're using, right? At any given point, there will be an x value, and the y value is just whatever f of x is, right? And we already said that the height of one of these rectangles is just that y value. So the height is actually pretty easy as well. The height is just going to be f of x sub I, and I'm going to put like a little star here because that's what you'll see. This is what you see in the textbook. And this isn't meant to scare you. I'll highlight it. This x sub I star just basically means like this, you know, this x value depends, right? Depends on what method we're using, right? If we're using the left Riemann sums, the right Riemann sums, or the midpoint Riemann sums, and what our interval is, okay? And what our interval is. But you can imagine, okay, going back to this drawing over here, that if I cut this thing up into pieces, this would be like the first x value maybe, that would be like the second x value, and that would be the third x value, and dot, dot, dot. And so that's why they use this x sub I notation right there. They basically just say, look, if you're using the left Riemann sum method or the right Riemann sum method, like whatever method it is, pay close attention. The height is just the y value you get at that point, and the width is also equally easy to obtain. So you'll see this very generic formula kind of when it's all said and done, put together. You'll see n is equal to 1 to big N, and then they put in f of x sub I. They put a little star here, which you can ignore, and then multiply it by b minus a over n. And this all just stems from the fact that we're just adding up the height times the width, right, for a whole bunch of different rectangles, right? And so, you know, these are each individually just a sub n's. They're all the individual little tiny rectangles that we're going to find the area of. One more tiny bit before we kind of close this video off is this part, the width. You may remember that in calculus, we call an infinitely small change in x dx. Well, in calculus 2, we call a small change in x that we can measure, we call it delta x. And so this delta x is a small, what I'm going to call measurable change in x. So another way that you may see this formula show up in the textbook, if you do some reading on your own, which you should, is you'll see f of x sub I, and then you'll see multiplied by like delta x, right? And again, this is still, this is just the height, this is just the width, et cetera, et cetera, et cetera. Very easy to kind of keep going. And yeah, so I think we're gonna stop this video here. Okay, there's a lot going on. And so let's kind of go back, let's kind of scroll all the way back up and kind of see where we're at. So the point of this video was to learn about Riemann sums. It was to tackle the question of how could I come up with the area underneath this function. In this particular case, x squared was the one that we were using. And it was how could I find the area underneath x squared on a certain interval. I said, just forget why I'm asking you it. Let's just try and tackle it. We started off by with one rectangle, then we did 2 rectangles, then we did 4 rectangles, and we said the more rectangles that I add, the better it kind of seems that this guess is getting. And so we had to introduce some notation, this sigma notation, which was like a way of shorthanding all of this, so I didn't have to write down A1 plus A2 plus A3 plus A4 every single time. And then we just said, all right, well, this concept seems pretty easy. We're just drawing rectangles, which is all we're doing. We're just drawing rectangles. We use the left Riemann sum if we're going to say, all right, look, here's an interval. Where do I want to draw this rectangle from? I'm going to use the left endpoint. Okay, here's the interval on this one on the right. I'm going to draw it using the right endpoints. Okay, here's the intervals for these particular rectangles. I'm going to draw them using the midpoints. And that is pretty much just what those 3 methods are. They're just going to give you different approximations of the same thing. Is one better than the other? Like it kind of just depends. You may look at the midpoint one and be like, oh, the midpoint one is the best. I could come up with a whole bunch of examples that show you where that kind of goes off the rails. Yeah, for now we just have a few different methods. And then we just revisited sigma notation one more time to kind of, get into these wacky formulas that you're going to see in the textbook if you do some reading on your own or you look at some of these examples. And this is pretty much where we're going to leave the video. So just the final notes one more time is that this idea of Riemann sums is approximating the total area under f of x on some interval, right? Some interval from x is equal to a all the way to x is equal to b. Okay, and I implore you, I know there's going to be a lot of crazy notation that you're seeing right now that probably is going to scare you. If you have questions about this, post it in the discussion, come to office hours, ask me or things like that. But what you should focus on is just the very bare bones basic idea. I think this part of the entire video is the best. This is what we're focusing on. We're just drawing rectangles. And if you're asked to do this, we're just drawing rectangles no matter what this interval is, no matter what these numbers are. I know all of you can add up areas of rectangles. We can do this in geometry class. I know you can do it right now. So that's where we're going to cut this video. If you have questions, again, post in the discussion. And then when you're ready to kind of move on, head on to the next one.